Okay, so doubling back to our spider on a Roomba example. We showed that we can write our position vector in terms of multiple reference frames. So we can write the position of the spider with respect to the origin in frame A as u of A1 plus v of A2 plus r of B1. Okay, so we have multiple reference frames used here. And then next we needed to take the velocity of this position vector, so point S in frame A, so of course that's dA dt, so of u A1 plus v A2 plus r B1. Now, taking the time derivative in frame A of the two terms that have A1 and A2 in them is easy, right? So we can just separate those out. As shown here. And we'll keep this term that's written with respect to frame B separate. So this is easy. We just have u dot A1 plus v dot A2. And this here was the tricky part, right? So in the last video, we said, oh, well, we can actually just substitute. We know how to write B1 in terms of, like, we could do this. We could write B1 is equal to r cosine theta A1 plus r sine theta A2, and then we were back to pretty much where we started. But in this video, I'm going to show you that there's actually a formula, which we call the magic formula, which allows you to find the time derivative in a fixed frame, so fixed frame A, of a vector that's presented in units of a moving frame, like frame B here. Okay, so here it is, the magic formula. For any vector v that is presented in unit vectors of frame B, we can write the following. We can write that the time derivative of that vector in frame A is equal to the time derivative of that vector in frame V plus the cross product of the angular velocity of frame B in frame A with that vector. Okay, so with this here, this magic formula, we can calculate what this derivative term is here. And we don't have to do that substitution, right? We don't have to rewrite RB1 in terms of A1 and A2. All right, so now let's demonstrate how we use this magic formula to solve for this term here. So we want to get the time derivative of RB1, which is a vector that's written in terms of the unit vectors of frame B, so that's a good check there. And we want to get that in frame A. So just so you know what I'm doing, I'm essentially plugging in to our magic formula that V is equal to RB1. So to write this out, we have the time derivative of RB1 in frame B plus the cross product of the angular velocity of frame B in frame A with our vector RB1. So the first thing you should remember is from, I think, 2 videos ago, is that the angular velocity of frame B in frame A is equal to theta dot B3. And so we can plug this into our equation, and now we can rewrite this as follows. So first we can take this time derivative, right, of RB1 in frame B. That's easy. That's just simply R dot B1. And then we plug in our angular velocity. So we have theta dot B3 with our cross product with our B1. Now, I hope that you're all familiar with the cross product. If you're not, that's okay. It's easy to catch up on, and you can also let me know, and I can make a video explaining it. But essentially, when you take the cross product of 2 vectors, you're finding the vector that is perpendicular to both of those vectors. So if you think of, say, if you have 3 orthogonal vectors, like you do in the case of B1, B2, B3, right? So if you were to draw that out, we typically look at, right, B1 and B2, but B3, which is coming out of the page, is also orthogonal to, and perpendicular to both B1 and B2. So that's a long way of saying that, you know, taking the cross product of B3 and B1 is going to give you B2. So you can actually write this as R dot B1 plus, and then you multiply these terms, R and theta dot B2. And this now is your derivative of RB1 in frame A, but you are still writing that in terms of the unit vectors of B, right? So you can just plug this in here. So you don't have to go through the process of, like I said, writing B1 in terms of A1 and then taking the derivative. You can simply use this magic formula and you can solve this derivative. And now, just for completeness, I'm going to write this out. So we have our velocity of point S, our spider in frame A is equal to U dot A1 plus V dot A2 plus R dot B1 plus R theta dot B2. In the next video, I'm going to go ahead and derive this magic formula so that you know why this is true. And then after that, I'm going to start from scratch, and we're just going to run through the whole spider on a Roomba problem, solved all the way through using the magic formula.